Imagine a big library where many children want to look at the same picture book. Some children only want to read, they do not change the pictures, while a few want to draw new pictures on the pages, they change the book. If a child is drawing, nobody else should read because the picture could be half-finished and look weird. This is the reader's-writer's problem. In a kitchen, 5 philosophers sit around a round table, each with a bowl of noodles, but there is only one fork between each pair. To eat, a philosopher must hold both the left and the right fork. The dining philosopher's problem asks how they can all eat without fighting over forks. The problem is needed because computers have many programs, processes that share the same data or devices, and we must tell them when it is safe to use the shared item. Formally, we describe a set of processes P equals the set containing P1 through Pn, and a set of resources R equals the set containing R1 through Rm. Each process has a request and a release operation on a resource, and the specification says, no 2 writers or 2 philosophers using the same fork may be in the critical section at the same time. Any number of readers may be in the critical section together, as long as no writer is present. A philosopher may eat only if it holds both adjacent forks. These rules make the problem precise so we can design correct solutions. When we talk about a solution being correct, we check 3 main ideas. Mutual exclusion means that 2 things that must not be together are never together, like 2 children not drawing on the same page at the same time or 2 philosophers never holding the same fork. Consistency means the shared data stays right after everyone finishes, the book still looks like a proper story, and no fork is magically in 2 places. Progress guarantees are about fairness. If a child wants to read or write, or a philosopher wants to eat, they will eventually get a chance. This is called no starvation, nobody waits forever, and no deadlock. The system never gets stuck with everyone waiting for each other. In simple words, the system should always move forward and never freeze. We can solve these problems with a few classic tools that act like traffic lights for the processes. A semaphore is a counter that tells how many tokens or places are free. Think of a box of crayons. When a child takes a crayon, the count goes down. When they put it back, the count goes up. If the count is 0, the next child must wait. A monitor is like a guarded room with a custodian. The custodian lets only one child enter the room at a time and can also keep a line queue of waiting children. Inside the monitor, we can write special code that lets many readers in together but blocks writers. A read-write lock is a special key that has 2 shapes. A red shape that many children can hold at once, and a write shape that only one child can hold, and that blocks all reads. These tools help us make sure the rules from the previous point are always followed. Explanation: sometimes the children or philosophers get stuck. Deadlock is like a circle of kids each holding one fork and waiting for the next fork. No one can move. Starvation is when one child never gets a turn because others keep jumping ahead, like a line at a slide where the same few kids keep cutting in. Livelock is when everyone keeps moving but never makes progress, like 2 kids shaking hands forever instead of letting go. To avoid these, we can give the forks an ordering. Always pick the left fork first, then the right, so a circle cannot form. A butler and extra semaphore can allow at most 4 philosophers to sit at the table, leaving at least 1 fork free. This breaks deadlock. For starvation, we can use a queue that serves requests in the order they arrive, or give a little priority token to a waiting writer after a certain time. These tricks keep the system moving and fair. Performance tells us how fast the system works. Throughput is the number of completed operations per second. If 100 reads finish in 5 seconds, throughput equals 100 divided by 5 equals 20 reads per second. Latency is the average waiting time for one operation. For example, if each child waits 0.2 seconds before getting a crayon, the latency is 0.2 seconds. Contention happens when many children want the same resource at the same time, which makes the waiting time grow. Mathematically, if lambda is the arrival rate of requests and mu is the service rate of the resource, the utilization rho equals lambda divided by mu. When rho approaches 1, contention is high and latency spikes. Think of a busy checkout line. Understanding these numbers helps us pick the right synchronization method. A simple lock may be fine when rho is low, but a read-write lock helps when many reads. High lambda for reads dominate. Explanation: a fair system treats everyone equally like a line at a candy store, where the first child in line gets the candy first. In the reader's world, reader prefer policies. Let readers keep coming while a writer waits, which can starve the writer. Writer prefer does the opposite, possibly slowing down readers. A fair or alternating policy uses a queue, so the first request, whether read or write, is served next. For philosophers, fairness means each philosopher eventually gets both forks. We can give each philosopher a ticket number, and let the one with the smallest number eat first. Some systems also give priority to urgent tasks like a fire alarm that lets the firefighter thread run before others. Explanation: to be sure our solution really works, we write invariance statements that are always true. For the writer's problem, one invariant is W equals 1 implies R equals 0. If one writer is inside, the number of readers R must be 0. Another is R greater than or equal to 0. W belongs to the set 0 to 1. We prove these by induction on each step, show they hold before the program starts, and that every allowed operation acquire, release keeps them true. For dining philosophers, we use the invariant. No fork is held by two philosophers at the same time. Mathematically, for each fork f, the sum of holds h of f is less than or equal to 1. State space reduction means we group together states that look the same for the proof, so we only need to check a few representative cases. Tools like model checkers can automatically explore all possible states and confirm that no deadlock state is reachable. These ideas are not just puzzles, they appear everywhere. Databases use writer's locks so many users can read a table together, but only one can update it. File systems let many programs read a file, while a backup program writes new data. Web browsers cache pages with read-write locks, so many tabs can read the cache while the network thread updates it. In operating systems, the kernel protects data structures with spin locks, a kind of semaphore. A classic case study is the Linux rwlock implementation, which gives good performance for mostly read workloads. Another is the philosopher-Butler algorithm, used in real-time embedded systems to avoid deadlock when several tasks need the same hardware peripheral. Finally, we can compare the main algorithms. A simple mutex single lock is easy to code but blocks all readers when any writer arrives, hurting throughput for read-heavy workloads. A read-write lock lets many readers run together, improving throughput, but can be more complex and may still cause writer starvation if not designed carefully. Optimistic concurrency, for example versioned reads, lets readers proceed without locking and checks at the end if a writer changed the data, good when conflicts are rare. For philosophers, the resource hierarchy method, always pick forks in a fixed order, avoids deadlock with little overhead, while the Butler limit number of diners adds an extra semaphore but is simple to understand. The trade-offs are usually between simplicity, speed, and fairness. Simpler solutions are easier to verify but may waste time. More sophisticated ones give higher performance but need careful design to keep them correct.